Hi, in this video I'm going to be discussing carbon-13 NMR. So what is this? Carbon-13 is an isotope of carbon and NMR stands for nuclear magnetic resonance. Let's quickly draw out our example molecules that we're going to use in this video. So ethane, and let's use bromoethane. So let's briefly discuss the theory behind how NMR works. So all nuclei have a spin, and the molecules absorb radio waves, which flips the spin from a low energy spin state to a high energy spin state. Carbon-13 solely focuses on the carbon atoms in each molecule, so in this case the two carbon atoms in ethane. Hopefully you can see that there's only one carbon environment in this molecule. This carbon atom here is bonded to 3 hydrogen atoms and a methyl group, and also this carbon atom here is bonded to 3 hydrogen atoms and a methyl group here. So when it comes to interpreting the spectra for ethane, chemical shifted on the bottom in parts per million, which is ppm. They use parts per million because it's such a small difference. Slight parts per million. So we can expect to see one peak because there's one carbon environment, and then we refer to the chemical data sheet. Using the chemical data sheet, we can look at what structures are found at certain chemical shift values. So chemical shift values like the amount of energy needed in parts per million to flip the spin state of the nuclei in that certain group. It's like a benzene ring or an alkyl group or an alkyl halide group. So our molecular example here, ethane. So if we're looking at a typical spectra from ethane, we've got chemical shift on the bottom, 0 on the right, and then we're expecting one peak due to the one carbon environment. So then we refer to the sheet and find the structure. So it's an alkyl, which is within the region of 10 to say 50 ppm. So I'm going to place a single peak, so about 20, and that's a typical spectra for ethane. So looking at the spectra for bromoethane, you can expect to see 2 peaks. 2 different carbon environments are equivalent to 2 different peaks on the spectra. So then, same as last time, we refer to the guide, and we've got an alcohol group, which is going to be a similar position to this. So, place that about 20. This is a rough estimate, the figures, but it's within the region. And then we've also got an alkyl halide group. I'll place that about, which is in the region on the guide from 10 to 60. So I'm going to place that about 50. So we've got 2 different peaks representing our 2 different carbon environments, and then we look at the chemical shift value, refer to the data sheet, and we can identify what group is at that particular region of chemical shift value. Okay, let's now look how you'd go about running an NMR experiment. Test tube, and then into this test tube you need to add your sample mixed with a solvent, and I'll get on to which solvent you'd use in a minute. And you also add TMS, which is tetramethylsilane, and the structure of TMS follows. Why is TMS used? TMS is used because it requires the most amount of energy to flip the spin state that can be used as a standard. So when we have our spectra, it gives us 0 on the right, this is the most amount of energy, and then anything else, like our sample, will be to the left of that TMS value, because less energy is required to flip the spin, so we'll get values to the left of the TMS value. The commonly used solvent is CDCl3. The D stands for deuterium, which is an isotope H2 of hydrogen. So why is it used? H2 does not have a spin, so therefore no signal will be shown for this solvent on the spectra, so that will reduce confusion with other peaks. In rare scenarios, they may add the peak on, so be careful, watch out for a peak at 77 parts per million, because that's often CDCl3 solvent. Hi, I hope that was a good introduction to Carbon-13 NMR, and I really hope you enjoy and benefit from the upcoming video on Proton NMR.